In this video, we will examine how the special theory of relativity predicts that time goes more slowly for bodies in motion than when at rest. This effect is known as time dilation. In his book on relativity, Einstein makes this statement: as a consequence of its motion, a clock goes more slowly than when at rest. In his book, he sets up a thought experiment to demonstrate this assertion. He asks us to imagine a clock which is permanently situated at the origin x1 equals 0 of k1, where k1 is a coordinate system moving at a velocity equal to v relative to the stationary coordinate system k. He then states that t1 equals 0 and t1 equals 1 are two successive ticks of this clock, so that the elapsed time between these two events, as judged from the k1 moving coordinate system, is 1 second. He now asks us what is the elapsed time as judged from the stationary k coordinate system. We will now answer that question. We need to determine the time of the first event relative to the k system and the time of the second event relative to the k system. In this example, we have selected an arbitrary value of 60 meters per second for the relative velocity. We employed the Lorentz Transformation to calculate these times. We should note that we normally write the transformation like this when we know the values of the stationary coordinate system k and want to calculate the value of the moving system k1. But in our case, we want to calculate the value of the stationary system k. So we move the k1 coordinate values to the right of the equation and the k coordinates to the left. We also need to change the sign of the velocity v from minus to plus. So we use this equation to calculate the time of the first event as judged from the stationary reference body. By definition, x1 is equal to 0. Therefore, the expression v times x1 divided by c squared also equals 0. And t1 is by definition equal to 0. Therefore, time t for the first event equals 0. Turning to the second event, this expression is again equal to 0 for the same reason. We now calculate the values of v squared and c squared and divide v squared by c squared. I have used a value of 300,000 meters per second for c. This is not the exact value, but has the merit of being that quoted by Einstein and is near enough to make no significant difference. The result of v squared divided by c squared is subtracted from 1 and the square root is calculated. t1, which is equal to 1, is then divided by this result. So we find that the elapsed time between the two events is slightly greater as judged from the stationary system than when judged from the moving body of reference. We note that the time difference between the two coordinate systems is very small, at only 0.502. Nevertheless, this result confirms Einstein's assertion that a clock on a moving body of reference goes more slowly than when at rest. To obtain a fuller understanding, we can work through some more examples. We will first pause, however, to derive a general equation regarding the relative times between two events. In deriving the general equation, we will adopt the convention of making gamma equal to the Lorentz factor. In this way, the transformation for time can be written like this. It is helpful if we adopt a further convention. This is to suffix t and t1 with a for the initial event and with b for the second event. Based on these conventions, we can write the time equations for the first and second events. The elapsed time is given by subtracting the time of the first event from the time of the second event. Having done so, we see that both components on the right side of the equation are multiplied by gamma. We can therefore simplify. We now see that we have a positive and negative expression. These are equal in value, as the relative velocity v is by definition constant, as is c, the velocity of light. And x1 on the k1 coordinate system is also constant. I should point out that this does not depend on x1 equaling 0. It applies for any value of x1. These two values therefore cancel out. And this effectively gives us the general formula for comparing the elapsed time between two events. It says that the elapsed time, as judged from the stationary coordinate system, equals the elapsed time as judged from the moving coordinate system, multiplied by gamma, the Lorentz factor. If we align this equation with the k and k1 coordinate systems, we can write the equation like this.